Moving from correlation to basic regression, remember that simple regression is simply measuring a linear relationship between two continuous variables. So data points are organized like those in a Pearson correlation. However, beyond the correlation, we now actually do the prediction line. So that line of best fit is being drawn mathematically to fit those scores. And that line is being drawn in such a way to minimize the amount of residuals or error. So whatever the line is that has the least amount of error is the line that we draw. And that line is then what we're actually gathering our information about the actual strength of the regression or correlation. Again, linear regression fits that data to a straight line, and if we have reason to believe that it is not a straight line, it's curved, i.e. we looked at the scatter plot and saw that there seemed to be a solid relationship, but it wasn't a linear one, we can adjust through multiple regression to look for a curvilinear relationship. And usually we're going to be doing that through multiple regression because we examine the relationships between several predictors, which means that we can actually look at both the linear model and the curvilinear model in one analysis. And of course, the question is even if it looks like it's curvilinear, do we actually get a better prediction by using a curvilinear prediction? It may turn out that though it's slightly curved, a linear regression is still a stronger and better predictor, less residual error than the curvilinear one. So really the best way to test for a curvilinear regression is through multiple regression, where we put the linear term in the first block and the curvilinear term in the second block. In other words, we ask the question, after we've accounted for the variance of a linear model, is there any variance left significantly, a significant amount left to explain a curvilinear? And if we find the curvilinear relationship is significant after already accounting for the linear relationship, that's usually a very good indicator that the curvilinear regression is a better fit for the model than the linear one. So again, just a quick reminder, when we're interpreting the regression coefficients, we're basically doing a equation where we actually have a one-to-one relationship. For any point in a line of x, there will be a corresponding y. And the equation is both a theoretical one and a practical one. And the only difference is the theoretical one includes the fact that there's error as an abstract term. Now, we can calculate error post-prediction through the use of residuals. But for the most part, when we're actually predicting, we're predicting y hat, which basically represents the predicted equation, accepting that there's error. And that's the practical equation that you see to the right. And again, the y-intercept, or a, is the constant. It's where the regression line would cross the y vertical axis. In other words, it is where would it be if x had no value. If x was 0, what would be y? And that's our start point. And that's rarely a 0. It's usually a number. The slope is the change in y per unit change in x, and it can be both positive and negative. And then we simply multiply someone's individual score on the predictor by the slope plus the constant to get their predicted score. So again, when we're doing regression, we're not going to report R. We're basically going to report beta and B. So B is similar to R, and beta is a standardized coefficient similar to R squared. So both of these are determining the strength and the direction of the relationship between X and Y. B weight, often referred to as small b or large B with the word weight after it, is the actual slope. It's the unstandardized coefficient. So the B weight is what we actually use in the equation. The beta is the statistical test statistic that we're calculating to determine if there's statistical significance. So an example, if our DV is creativity, IV is hours of reading fiction, there is a positive relationship between creativity and hours of reading fiction. We could calculate someone's score, their creativity, based on the number of hours they read science fiction. So in this case, we find out they spend 1.5 hours a day reading science fiction. I'm sorry, that the actual B weight is 1.5. In other words, for every hour spent reading science fiction, you actually get an increase in creativity. And if you don't read any fiction, your start point on creativity, in other words, an x of 0 is 6.4. So if I read, for example, 10 hours of fiction, 10 times 1.5 would be 15. 15 plus the constant of 6.4 would be 21.4. That would be my predicted score on my DV of creativity. That would be y hat. So to make a prediction from an unobserved outcome from an observed predictor, we simply plug the x value into the equation and solve. So The example I just ran through on the last slide is just shown here physically. If Daniel spends 10 hours of reading, how creative would you expect him to be? We'd expect him to get a 21.4 on our creativity scale. And we'd also want to report not just our prediction, we'd also want to report why we trust that prediction. We'd report the beta, and that's basically the overall test score. That's our actual tested, calculated test statistic, 0.52. We'd report the B weight, or small b, 1.5 increase in our outcome for every unit of our predictor. And then we'd actually test if it's significant, and that's where we get a little bit different than with an R test. So if we're running a straight correlation with R, we can actually use that R to find out if it's significant or not. With a regression, we need to actually test each B weight separately, and we test it with a t-test. And then if that t-test is actually significant, we can claim statistical significance. And the reason we're doing this is that we need an ability to test each individual predictor in multiple regression. So we wouldn't actually need to necessarily do this if all we're doing is a simple regression with two predictors. But because we're going to use this technique if we have multiple predictors, we just go ahead and start with it whenever we're running a regression. So significant testing with R, so R and beta are going to be the same. However, with R, in a simple correlation, we can simply take that R and look at a probability chart, find our p-value, our alpha of 0.05, and find out what is the minimum R we need to claim 0.01. In the case of a regression or multiple regression, we're going to take our beta and we're going to then ask, is it significant? Is our correlation due to a true relationship of the population, or is it simply sampling error? So for example, our R or beta might be 0.26 with an N of 60. Our hypothesis, our alternative hypothesis, is that R is better than 0. Our null hypothesis is that R is 0. So again, to reject the null hypothesis indicates a significant correlation. Not a strong test, but very few things are completely unrelated. So just also recognize that generally that's why you'll see that low R's are often still insignificant, because for the most part, we rarely find an R of 0 in anything, including things that truly aren't correlated, simply due to error. So how we're actually going to calculate this is the following equation. We're going to take the R, or beta. We're going to take the N of the sample minus 2, and we're going to take the square root of that and multiply it by R. That's the top of our equation for T. The bottom of our equation is going to be minus 1 minus R, or beta squared, and again, the square root. Our degrees of freedom is N minus 2. So this is how we calculate T. Once we have the T, we simply go to a T-chart with the degrees of freedom of N minus 2 and find out, did we make the required number for statistical significance? So in this particular case, we have an N of 60. So, and we have an R of 0.26. So we take 0.26 times the square root of 60 minus 2, and we divide it by 1 minus 0.06276, that's R squared, and again the square root, and we get a T of 2.05. Our degrees of freedom in this case for this test is N minus 2, so 60 minus 2 is 58. Our alpha is set at 0.05, and we find out that the critical T for an alpha of 0.05 with a DF, degrees of freedom of 58, is 2.009. We found 2.05, slightly above, so it is statistically significant. The next thing we want to look at is goodness of fit, and that's with confidence intervals. So confidence intervals allow us to kind of determine how plus or minus is our guesses likely to be. So I have the equation for C, the standard error of the estimate, and again, it is calculated by actually knowing on a previous sample what was our prediction versus what was the actual score. So you can actually run a standard error of the estimate on your initial sample. You could also gather it from a future sample, but you still need not only the prediction, but what they actually scored. You subtract each person's actual score from the prediction, squared, add it all up, divide by the total number of scores minus 2, and then take the square root. That provides you the standard error of the estimate. Now your confidence interval is your prediction plus or minus the C, standard error of the estimate. So that gives us, this is what we predict, plus or minus this value is most likely where that person is going to score. Obviously, the smaller the SEE, standard error of the estimate, the more likely or the more trustable that prediction is. The bigger the standard error of the estimate, the less less accurate that prediction is going to be. Once again, we're going to calculate R squared for each predictor. Total variance accounted for in predicting the outcome of Y by the predictor X. And once again, 1 minus R squared is a total variability not accounted for. R squared is an effect size, and it's simply Pearson R squared, or beta squared will get you the same information. Remember again that beta is still an omnibus test for a particular predictor. It's simply referring to the fact that we're using regression now instead of correlation. And the reason we use a different notation is to let people know we are using a different test with a different purpose.